Today we will discuss about sentiment analysis machine learning project in which we will create a machine learning model which can analyze tweets on Twitter and understand or evaluate what sentiments are behind the words. To do this, of course, we will have to create an NLP model. Natural language processing is a very new field which has been booming in recent times. Mainly, it is used for customer review segmentation on various websites, and so it's pretty new. There are obviously the following use cases for it. The requirements for creating such a model are, first of all, when you take data in the form of a CSV file, you have whole statements or paragraphs put together in one row, and a machine, first of all, cannot understand words and forget forget sen- forget words. It cannot forget sentence forget I mean, it cannot understand words, and and if it cannot understand words, obviously it cannot understand sentences. So first we need to break down the sentences to words and then convert the words to numbers or vectors, after which we can then train our model to analyze the numbers that we have given it against the sentiments in our training set, and it will then run a few iterations until it is finally capable at analyzing the data it receives itself in word format, able to convert it by itself into numbers and analyze it and be able to say, okay, that's the sentiment being used here. Okay, the person is happy based on, because the numbers were like this, we understand that the words are like this, and because of this word appearing, uh, i'm I'm glad, for example, glad appearing, so now I understand that the person's sentiment behind this sentence is happy. Or I don't know, that's a negative sentiment because don't know, person is unhappy on being ignorant on some topic. Now, there are certain challenges which you face in creating such models. First of all, to make your machine learning model understand sentiments, you need to give it a lot of data, because there are a lot of sentiments. You can be happy, you can be worried, you can be upset, you can be angry, you can be right. So there are, you can be disgusted, there are many sentiments. So to train a model which should be able to give you that accurate analysis of sentiments, you need a lot of data, which will result in a lot of processing time and a lot of computational power. So we won't be going that much in depth, we will just be predicting whether the sentiment behind this tweet is negative or positive. Now, the technicality is we'll be using Word2Vec and LSTM. LSTM is, of course, a neural network model, and Word2Vec is, of course, used for converting the words to vectors, which is clearly in the name. There are other ways you can do this. Some are better, some are worse, but mainly we are going to use these methods because LSTM till quite recently, till literally I think 2018 or 2020, was the best method out there for doing sentiment analysis. The methodology is simple. We will get data from Twitter via the CSV file, but in real time, you should be doing web scraping, which we will cover in a future video. Remove stemming, I mean, implement stemming and remove the stop words. I will explain this later. Implement train test split. We are keeping the training data 80% and the testing data 20% for optimum training. Implement Word2Vec tokenizer. Fine. LSTM. Our accuracy will be around 92%. That's like what we are expecting. Now, tokenization. Tokenization is simply you take a whole statement. Okay, now there are steps. First, you need to remove stop words from the statement. Stop words are simply words which are not that required. Like which are not giving much information. Like a computer science portal for geeks is the example given here. Now, or for they're not giving you much information. And a machine learning model does not require sentences like humans. It requires keywords, main important words which it can use to analyze. So for, the, these don't make much of a difference as for, can. No. Stemming is when you reduce a word to its stem. You have examples here. And then tokenization is after you have removed the stop words and done stemming, and then you convert those sentences into one word per row. So simply what this does is makes it more easier, for the machine to understand, because it gets single number inputs. Word2Vec is Word2Vec is a very effective way of capturing the semantic meaning behind words in such a way that the machine is capable of understanding which words are similar based on the vectors it receives. So we are converting the words to vectors for the machine, right? We were doing that before, TF-IDF, as we saw in our fake news detection project. We were doing it there as well. But TF-IDF cannot tell you which two words are similar. It won't know cat and kitten are similar or man and woman are similar. It won't know that, right? But Word2Vec is capable of doing that, and how it does it is it does not just randomly assign a vector or multiply the number of times it appears with the number of times it appears in other documents. What it does is it assigns a list of features. So, for example, living being, feline, human, gender, royalty, verb, plural. It takes all these features, and then based on those features, it gives a rating, a probability rating of that feature being true for the word in case. So, cat, is it a living being? Yes, dot 6. Feline, yes, dot 9. High. Human, no, dot 1. So based on that, it gives those ratings. And then these ratings, there are like, it does not give you one or two features, right? These features are like 7, 8, more than that. So these features are then converted into two-dimensional vectors, simply two values like 31, 72. These values are capable of making the machine understand these features, and thus understand which two words are similar by comparing the features of one word to another. So it can now understand, okay, cat, kitten are similar, and cat is also similar to dog. Not as similar as it is to kitten, but it is similar. Houses and cat, no, not same, quite different. Another thing that it's capable of doing is it is capable of using maths or com- com- computing logical functions on words. So like you can say you can say woman plus or king minus man plus woman, right? So it will be able to subtract the feature values, and it will get a feature value which will be quite unique and will actually be the feature value for queen. And so it will be able to do such logical tasks, which is amazing, because TF-IDF and previous um, uh, were text embedding algorithms couldn't exactly capture this part of semantic meaning before. And so it's very new that model is able to capture that. So the way one of the way two algorithms which are mainly used in Word2Vec are continuous bag of words and skipgram. So simply continuous bag of words takes the context and tries to make a relation, logical relation or linear relation, tries to understand the linear relation between the context and the target word. It selects the target word on its own. And then there is skipgram, which does the opposite. It takes a target word and tries to understand the relation between the target word and the context. So it's simply trying to take the context and predict the target word, and take the target word and predict the context. And this is what trains the model to understand which words are similar, which words go with each other, right? It is mainly used in autocomplete on Grammarly and Google, and all these autocomplete platforms mainly use this technology. Label encoder. Okay, label encoder is simply when you have a categorical variable with 8 9 categories, and if you one hot encode them, you will have so many. And because it's just the y variable, it's not a feature. See, if it was a feature, you will have to one hot encode it categorically. I mean, if you label encoded it into 0 1 2 3 4 5 6, you would run into some problems. Like, for example, it will start making strange assumptions with the numbers. But with your target variable, because there is only one target variable, what happens is it does not make such assumptions, and the target variable can be label encoded. So label encoding simply maps an integer value to our categories. LSTM. LSTM, or long short-term memory. So what long short-term memory means is all neural networks have a short-term memory. Mainly, like, not all, but recurrent neural networks, because they're constantly, see, once you give an input, it applies an activation function, a sigmoid function, and using this activation function, it gets an output, right? This activation function is in the hidden layer. Now what happens is, over time, as new inputs are processed and new outputs come out, it back propagates and adjusts the weights and the activation functions to better be able to predict the outputs. This happens in the training phase. So, but what happens in recurrent neural networks is, while back propagating and training, what happens is it changes the activation function so many times that the important features which should have been stored are not stored. So, like, if you had a statement like Thor's hammer is named Mjolnir, right? So by the time it will reach Mjolnir, it will have forgotten the word Thor. Now the word Thor is important because Thor and Mjolnir have to be mapped together, because they mean something, right? Because they this one thing is the owner and one thing is the object, one thing is the subject. So that is and then base for example, if I'm writing the sentence, the how I opened the. Now if it does not, if it forgot opened by the time it reached the, like, if it forgets the previous words, how is it going to predict the next word? For a statement to be correctly auto completed, the important words used previously in the sentence or paragraph have to be remembered. It is necessary. And so what LSTM simply does is, it also keeps a separate long-term memory cell in which it stores the important words and activation functions which can be required in the future. So it remembers the important features in this, and what how this will help is, it will remember which word will have a positive or negative impact in the past, and using that it can predict which, when that word comes again, that okay, this word I've seen it before, it had a negative impact. That's why we need LSTM. Confusion matrix is simply, it's a visual representation of cross entropy. Entropy simply means there are many types of error calculations. There is absolute loss, which is simply you just take your your predicted values, subtract them from the actual values, and that's your absolute error. Then there is mean squared error, where you average out the error. I mean, there is mean absolute error, and then there is mean squared error, where you take a mean, but before taking the mean, when you're subtracting the predicted values from the actual values, you square it so that the negative values don't end up cancelling the positive values. And thus, like, if you had an error of plus 10 on the first one and you predicted minus 10 on the second one, it will say, okay, plus 10 minus 10, your error is 0, and hence you have the perfect model, while in actuality you don't. So in reality you don't. So what mean squared error does is, because of that 10 and minus 10, it squares it. And what happens, because 100, okay, so your error is 200. You get higher values, but you can understand, right? What cross entropy does is, it simply takes the amount of times your model predicted. So binary cross entropy, first of all, let me correct myself, we're speaking about binary cross entropy. What binary cross entropy does is, it says, okay, how many times did you predict 0 and it was actually 0? So true negatives. How many times did you predict 1 and it was actually 1? True positives. How many times did you predict 0 but it was 1? So false negatives. And then how many times did you predict 1 and it was actually 0? So false positives. So using these 4 values, it will then calculate the error. So let's get to the coding phase. We'll be using Jupyter Notebook. So let's first just import the necessary modules here. You will see we are importing Matplotlib for the plotting of the confusion matrix, and tokenizer from Keras, all these important models. Okay, factor declaration. So what factor declaration simply means is there are values, right? There are parameters that you set when you're creating the LSTM model, the Word2Vec model, right? There are always some parameters. Now, rather than setting those parameters later, what you can do is you can just set it before. How that helps is simply, you can just you can call it later rather than setting it right there. And if you see here, we have given epochs 8. So what that means is in Keras we have given epochs 8, which is our LSTM value. Simply 8 iterations will be run on the training data. Batch size 1024, so at one time it's going to take 1024 records and train on it, right? We have given Word2Vec epochs. It's going to run 32 epochs on our words, right? So these are all the values that we require. Data exploration. So we are simply just loading our data and decoding the sentiments from numbers to words. Why we're doing that is just so that we can create this count plot and have a look at how many of our how many negative and positive records we have. So data pre-processing. So of course first we are removing the stop words. We will say stop words dot words English because we are removing all the English because we are referring to English, but you can use there are for other language tweets if you there are other language tweet stop words available. Stemming also English, and what we are doing is we are using this lambda function to apply this whole tokenization that we declared here on X, right? Because we just declared it here, but we did not apply it. So we are simply applying it on the entire X data, training data. I mean X data before we convert it, split it in training and testing, right? Because even the testing data needs to first be converted to a understand to a needs to be converted to a format where the machine model can understand it. At least it needs to understand the features before it can make predictions. And here we are just building our vocabulary, and we are Word2Vec underscore model dot most underscore similar love. Here what we are doing is we are asking it which is the most similar word to love that you found in the text, and it will give you like most probably or something very similar because it can calculate those values. It will be like, okay, love dot 41 this, like, okay, dot 398, okay, very similar. Label encoding, simply we are just taking all the unique values, saving them to a list, and then encoding those values with a unique integer value. Embedding matrix is simply used for to get our vectors embedded with a new set of weights, because we don't want integer values, we want values scaled, right? Because integer values are capable of what happens is simply the word with the larger integer values will be able to influence our model further despite actually not deserving any special importance. So that's why we will use embedding matrix, so that all our values are between 0 and 1 after the weights have been applied to them, and the model can then understand, okay, which word requires more importance, and then adjust the weights accordingly. Model creation. So here we are creating our model, we are creating our layers, right? LSTM, how much like we are creating one layer, which is one dense layer with activation sigmoid. Dense means where every neuron is connected to the other, and you can see here we have put our loss equals binary cross entropy. Optimizer is random. So optimizer is simply how you want your weights to be changed or your learning rates to change. We will go further into that in a later video. And we just said batch size equals batch size because we've already declared batch size in the what did we name it? Feature declaration phase, factor declaration phase. now we just compile our score, compile our score, and here in the bottom section we are simply saying if our sentiment score is less than 0.5, like if it's not, oh, like it should be at least 0.6 positive. Even if it is 0.5 positive, it is more than 0, so it's supposed to be positive, but you will still return negative because we don't want any error on the positive side. We are just trying to, like dot 3, many times you will get some statement which is slightly sounding positive but is actually more negative type. So okay, here we're just predicting and returning our labels and scores, elapsed time to see how long it took, and we are trying our prediction on the statement I love the music, which will be positive, obviously, but you can try more difficult statements to see how it reacts to those. And here we are first compiling our confusion matrix before plotting it. No, exactly. I mean, simply we are printing our classification report, which will consist of precision, recall, F1 score, support. These all, like precision is simply how accurately you predicted your positive values and all that. So in summary, there were 4 problems that we were trying to mainly solve, and we solved 3 of them with this method, right? I've written which method solved which problem. Which problem we did not solve was it does not know how to deal with emoticons. Now in Twitter, it won't be that hurtful because people still don't use that many emoticons on Twitter. But if you are trying to analyze either WhatsApp text or text messages, it will certainly hurt your model because you will have to because there are methods of dealing with it which we will cover in the future, right? Because you cannot just drop that. You can drop it, but you will lose some important data which could have helped your model become more accurate. Of course, there are still improvements, right? Like we could try BERT algorithm, and we haven't even dealt with the emoticons yet. But overall, this is, I think, a really good solution with a good 92% accuracy. And yes, I think it's a. So I think that covers it for this video.